Next week we have the lab test in lab. So I wanted to say a couple things about that. It's going to be, so what you're going to be asked to do, there's not going to be any using that software or timing, dropping things or anything like that. It's just going to be doing the kind of calculations you did in the labs. And any formulas that you needed in the labs to do the calculations are going to be given. So you just have to sort of understand how to use the formulas and answer questions like the questions in labs 1 through 3. The lab test is all we're doing in lab. It won't take most people the full time, but you can leave once you're done, and you have the full time if you want it. Yeah, you're taking it in your lab, so which is kind of a pain. You don't have to worry about that. That's my own problem, but it makes it a pain for me because I have to do all these different. I have to do 5 different versions of the same test, you know. But this isn't about me today. This is about. Okay, so just make sure you can answer questions like the questions asked in labs 1 through 3. And then some of you might think, well, what kind of questions can you ask about lab 2? Like labs 1 and 3 is the one this week. It sort of makes sense what kind of questions I would ask based on those. But lab 2 was that weird one that was all on the Excel spreadsheet, just asking like, how much of a difference did it make when we dropped lead from 1 meter, 20 meters? What was the difference in the time that it fell? So what about lab 2? So there's really, there's not going to be much about lab 2, but here are the kinds of things that I want you to be clear on. I want you to know that keeping everything else constant and increasing the mass reduces the effective air resistance. I want you to know that decreasing the surface area reduces the effective air resistance. And decreasing the speed reduces the effective air resistance. Okay, so let's think of that as all sort of one thing. And the second thing I want you to know and to never forget is that without air resistance, all objects behave the same way in free fall. So their acceleration is 9.81 meters per second squared down. And if you drop a flying squirrel and a sea elephant at the same time, they'll hit the ground at the same time. Okay? What's a sea elephant? Well, Sea elephant. I think that's an elephant seal. I think that's an acceptable alternative name, possibly. They look like this. You might think that would affect, you think that big nose might affect how they fall, but if there's no air resistance, it doesn't. Yeah. But not in a vacuum. Yes. But they can hold their breaths a long time. And the last thing, okay, is dropping objects from, well, we did 20 meters or less. Air resistance affects the fall time less than you thought. Probably. Less than you expected. If you didn't go to lab 2 and never look at lab 2 and just remember this stuff I wrote here, you'll be good for the lab test on lab 2. And then the rest will come from the other 2. Any questions about the lab test? If you want to take the lab test with a different lab, that's fine. Feel free to just show up to any of the other, I have 5 labs during the week. Feel free to show up to any of them. And I think that's all. So the next thing I want to do is just go through the test. I'll get it back to you on Monday. But let's just go through these problems. Okay, so tell me if this is a different one than you took. But so I have a rock is dropped off a bridge and takes 1.4 seconds to hit the water. That's not it? That's the wrong one. Hang it. I printed that one all out and everything. That's it? Okay. A ball is thrown straight up into the air from a height of 3 feet. Takes 3 seconds to hit the ground. What was the velocity when it was thrown? Okay, so it's thrown from here. The whole flight takes 3 seconds. This is 3 feet. What was the velocity at the instant it was released? The first thing we have to do is, well, we could do it in feet and seconds. I'm going to convert it to meters because that's what I'm used to. And I guess also because I either have to do that or the acceleration of gravity I have to convert to feet per second squared. So 3 feet, what's given? Oh, that's the wrong one. 1 meter is 3.81 feet. And so that comes out to be like, can someone tell me 0.91 or something? 0.94? Oh, 0.914 meters. And now time equals 0. I'm going to choose the instant that it's released. Time final is when it hits the ground, because we know the elapsed time from when it's released to when it hits the ground, and we know the location of the ground. Zero position. I always choose the ground or the lowest spot in these problems. So let's say the ground. And then positive direction, I'll choose up. We know time final is 3 seconds. We know the initial position is 0.914 meters. We know the final position is 0. We're trying to find the initial velocity, and we don't know the final velocity. And we know the acceleration. So P final is equal to P initial plus V initial time final plus 1/2 A time final squared. So we have 0. I'm gonna skip all the units in my calculations, but no, I'm not. But we're gonna start doing that after this. This is the last time I'm gonna show my units in calculations. That's like a historic moment. That's a good idea. Should we all get together for a selfie? Final unit selfie. There's a last time for everything. You know that they've been playing that song all the time by Brad Paisley. 0.914 plus 3 seconds times VI plus 1/2 times 9.81. I'm just going to write that as negative 4.905 meters per second squared. And then time final squared, so 3 seconds squared. So 0 is equal to 0.914 meters plus 3 seconds times V initial minus what's 9 times 4.905? No, I know, it's 39.24. Go ahead, check. If you don't believe me. Okay. Meters? Is that right? That was okay. No. Dang it. How did it go so wrong for me? Oh, I know why. So what do you get there? 14.715 meters. And so Oh, 44.145. Okay. And what's, okay, so now VI is equal to, what's 44.145 minus 0.914? Yeah. Yes, that's right. They're opposites. 43 something. 43 point what? 231. Yeah, I know that feeling. Except I usually do talk, and then afterwards I'm like, oh yeah, this is why I told myself not to talk before I came here. And then divide by 3 seconds. So what's 43.23 divided by 3? 14.41 meters per second. Okay, so does it make sense that that initial velocity is positive? Yeah, because it's being thrown up. So, and then it asks for it in millimeters per hour, scientific notation. Well, 1 meter is equal to, no, 1 millimeter is equal to 1 times 10 to the minus third meters. And 3,600 seconds is 1 hour. So 14.41 meters divided by seconds. So we'll have 1 times 10 to the minus third, and then 1 millimeter in the top. And then 3,600 seconds in the numerator, and 1 hour in the denominator. And can someone calculate that? $876,000 millimeters per hour. And so that's 5.1876367 times 10 to the 7 millimeters per hour. And then number 2, from the starting point A, a ball rolls 5 meters along the floor to point B in 7.5 seconds. Okay, so the ball's rolling this way. The distance is 5 meters. The ball just goes from here to here in 7.5 seconds. And time equals 0 corresponds to the start of the motion, so that means this has the time label 0, and this has the time label 0.5 seconds. And now we have to put the position labels on it. So if 0 is at B and the positive direction is the direction of motion, This is A, this is B. So then this is 0. The positive direction is this way. So if you start at 0 and go 5 meters in the negative direction, the label here is negative 5 meters. And so the motion goes from, you can think of that first instant as the coordinate pair 0, negative 5, and the second one, 7.5, 0. And we're just graphing those. So 0 and 7.5 seconds on the time axis. And for position, we want 0 and negative 5. So we'll go from 0, negative 5, that's this, to 7.50, that's this. So that's the position versus time graph. Any questions about that one? And then for the second one, this time the 0 position is at A, and the positive direction is in the same way. So we still have this same motion that looks like this. That's 0 seconds, 7.5 seconds. This time this is 0, and the positive direction's this way. So the label at that second instant, the position label is 5 meters in the positive direction from 0, so positive 5. So the coordinates are 0, 0. That's the first one. And the second one is 7.55. So it starts here and goes here. Any questions about that one? And then number 3, car is going 50 miles an hour and hits the brakes and stops in 0.1 minutes. How far does it travel? Yeah, yeah, sure. Oops.
Doesn't it say the positive direction is in the opposite?
Does it? Oh, does it? Opposite the direction of motion. Sorry about that. Okay, so positive is this way. And so that means this is negative 5. And so that's negative 5. And so it looks like this. Okay, number 3. So a car is going 50 miles an hour, hits the brakes, stops in 0.1 minutes. How far does it travel, expressed in meters? So this is what we want to find at distance. Here it's at rest. Here it's at 50 miles per hour. And the elapsed time is 0.10 minutes. So first let's convert to, we know we want to put everything in meters and seconds. So 50 miles divided by hours. 1 mile, I don't know what conversions I gave you. I'm not doing that one. So 1 mile is 1609.344 meters. And 1 hour is 3,600 seconds. So can someone calculate that for me? $22.352 meters per second. And then 0.1 minutes. 1 minute is 60 seconds. And so you get 6 seconds. And now time equals 0 is when the car hits the brakes. Time final is when it stops, reaches rest. Zero position, I'm going to choose the car's location at time equals 0. Because that's just a rewording of, that's an equivalent statement to initial position is equal to 0. And then the positive direction is the direction of motion. Time final, we know that. That's 6 seconds. Position initial is 0. Position final is what we're trying to find. Initial velocity is 22.352. Final velocity is 0. And we don't know acceleration. And so is there any equation that'll work with these? No. Yeah, so we have to calculate acceleration first. So we can use that simple equation to get that. So V final is equal to VI plus AT final. So 0 is equal to 22.352 meters per second plus A times 6 seconds. And so A is equal to negative 22.352 meters divided by seconds, all divided by 6 seconds. And what do you get for that? 3.725. Negative. meters per second squared. And so now we know the acceleration, and now we can use the P final is equal to P initial plus V initial T final plus 1/2 A T final squared. So P final is equal to 0 plus 22.352 meters per second times 6 seconds minus 3.725 meters per second squared times 6 seconds squared. And can someone calculate that? What? Yes. Yes, thank you. $122.937 meters. That's a long way. Those are not good breaks. Takes 6 seconds. That's too big, isn't it? Yeah. Yeah. 67.06. I'm surprised it's that big too. A lot. Any questions about that one? And then, I don't know, do we have to put it in some kind of funky form? No. That's it. And then the last one, a ball's thrown straight down toward the ground from a height of 15 meters. If its speed at the instant it's thrown is 5 meters per second, what's its velocity the instant before it hits the ground? I don't know, it's like Gru. I'm not saying. I remember though when I saw, I think it was the second Despicable Me, and the scene came on where they played Happy, and I was just like, that song is a jam. I still am not sick of it, I don't think. They did try to make everyone sick of it. Okay, so this is 15 meters. It's released with a speed of 5 meters per second. And we want to figure out the velocity right before it hits the ground. So time equals 0 is when it's released. Time final is when it hits the ground. Position equals 0 is the ground. Positive direction is up. Do we know the elapsed time? Nope. Do we know the initial position? Yep, that's positive 15 meters. Do we know final position? That's 0. Do we know initial velocity? Yes. And we know that the speed is 5 meters per second, but we have to combine that with what we know about the direction it's moving when it's released. It's moving down, which is our negative direction, so initial velocity is negative 5 meters per second. The final is what we're trying to find. And it's free fall, so we know the acceleration is negative 9.81 meters per second squared. I think this equation should work. 2a times the quantity p final minus p initial is equal to v final squared minus v initial squared. 2 times the quantity, negative 9.81 meters per second squared, times the quantity 0 minus 15 meters is equal to v final squared minus v initial squared. So you get positive 294.3, right? Yeah? Meters per second squared is equal to Vf squared minus 25 meters squared per second squared. And so Vf squared is equal to 294.3 plus 25. So what's that? 319.3 meters squared per second squared. And then take the square root, and V final is, so what's the square root of that? It's like probably 17.6? 17.869? Okay, so plus or minus 17.869 meters per second. And then we have the plus and minus because it's a square root. So the last thing we have to do is choose plus or minus. Which one makes sense here? Minus, because before it hits the ground, it's moving down. Yep. Okay. Yeah. Yeah, so this is, what's 22.352 times 6? And then what's 1/2 times 36, so 18 times 3.725. 67.05. And so this minus this. Oh. Oh, okay, yeah. Any questions about that? Okay, so I think, I feel pretty sure that I'll be able to get those and the quizzes that I haven't given back to you on Monday. All right, so that's the end of talking about 1D kinematics. Yes. It sort of depends what went wrong with the numbers, I suppose. I mean, it could be anywhere from not taking anything off, like I give full credit a lot of times if the numbers come out wrong, if it's just obvious to me that it was, you know, a, doesn't reflect any understanding of physics thing or whatever. But um, if there's just one mistake in there, the most the most you could lose is 2 out of 6. More likely 1 out of 6. It's but I sort of grade these. I don't really like take off points so much for mistakes. I more just sort of look at the whole thing and then give a score out of 6 based on how I feel like it looks like your understanding of that problem is. So that's kind of how I think of it. So if it looks like you understood it, great. You got all the directions right. That's 6 out of 6. Any other questions? Okay, so now we're going on to particle kinematics in 2D. Excuse me. Okay, so just a reminder of what all this stuff. So, what's a particle? Okay, yeah. So a particle is not. There's no such thing as an actual particle. It's a simplification we make, and when we make that simplification, we're treating something like it has no length and so no orientation. What? Location. Yep. Right. And kinematics, we still haven't done anything except kinematics. But kinematics is just describing the motion. Um, so we're not talking about causes of motion yet, like no forces or mass yet. And then, so now we're going from 1D to 2D. And the idea of 1D was wherever the object is, it only has 2 choices for directions to go. It can go forward or back. And so we can represent the directions with, so you can say there's 2 direction choices. And that works really nicely with positive and negative. And so that's why directional quantities in 1D are just numbers with positive and negative signs. 2D, particle here can go in infinitely many directions. So any direction in the plane, and obviously there aren't enough signs to specify directions in that case. We need a new mathematical thing to represent directions. So there's infinitely many direction choices. And so now we introduce this idea of vectors. And vectors do in 2D and 3D what signed numbers did in 1D. they give a magnitude and a direction. In 1D, numbers did that because their magnitude is the absolute value of the number, and their direction is given by a positive or a negative. When you're dealing with vectors, you can always represent a vector as an arrow. So that's the best way to think of it, is a vector is an arrow. The magnitude is its length, and the direction is the direction it's pointing. Okay, so those are all different vectors. A vector is just a mathematical thing. Let's say it's just a mathematical object. The same way a number is. So a vector itself doesn't have any units. You know, it just lives in the space of like math things. So it doesn't have its own units, but it is going to represent things that have units. But it will represent quantities that do have units. And that's exactly analogous to how numbers represent, you know, like the acceleration produced by gravity in most, if we choose a positive direction up, then it's negative 9.81 meters per second squared. We used a number as a way to represent the magnitude of that vector. And so now, so what kind of kinematic quantities are going to be represented by vectors? It's just all the ones that had direction in 1D. So vectors will now be used for all the quantities that have direction. So remember what those are? Time? So let's just go through the list of like all the quantities. So time, no, that doesn't have direction. Position, yeah. And so that's going to be a vector. And when we represent anything with a vector, we show that it's a vector by putting the little arrow over the top. Velocity. Oh, how about displacement first? Displacement has direction, yes. How about velocity? Yes. How about acceleration? Yes. Not time or distance or speed. There might be some more, but okay, so before we start talking about kinematics, so you know we're going to get into kind of the same definitions of all these things that we did in one dimension. I first have to define, so let me write that. Before we do 2D kinematics, we need vector math. And before we can do vector math, we need to talk about trigonometry. I know a lot of people have taken trigonometry, but it's not a prerequisite for this class, so I'm just going to give the basics that we need for this class. Probably be a nice review for a lot of people anyways. What? Okay, so I'm going to start by just talking about vectors, and then I'm going to explain what we need trigonometry for, and then I'll give a little intro to trigonometry. So a vector is an arrow, right? That's a vector. And magnitude is given by its length. And in order to do math with vectors, we're going to break it up into components. We'll express them as components. So what that means is if you move the tail of the vector to the origin of your coordinate system, and there's no problem doing that because a vector only has a direction and a magnitude. It doesn't have a position. So you can, without changing what a vector is, you can move it wherever you want. Okay, we're going to move it to have the tail at the origin. Then the components are the vector components are the coordinates of the vector's head. And another way to think of that is you can break this vector up into a path along the x-axis and a path parallel to the y-axis. Then these two, that path along the x-axis and the path along the y-axis are perpendicular to each other. And the lengths of those paths are the magnitudes of those components. So the components and the vector form a right triangle. And so that's why we're going to get into trigonometry. Trigonometry means studying triangles, and so that's the connection. Okay, so now we're going to talk about trigonometry. Whoever left me these notes, they really could be better. I'm just kidding. I'm the only one who's taught this class for like 10 years. Okay, well, this is what I'm going to do. So now we're talking about trigonometry. Okay, so find the vector components put the tail of the vector at the origin of the coordinate system. So let's say this time the vector is over here. So first, put the tail of the vector at the origin. And then second, find the counterclockwise angle from the positive x-axis to the vector. So let's say that in our example, we're given that this angle is 45 degrees. And the counterclockwise angle from the positive x-axis to the vector, that's not the 45 degrees. That's the angle from here around to there. So the way to come up with that is, I think a way that I like that always works is just keep hopping around from things that you know, like angles you know, to the next angle you know. If your jump goes counterclockwise, it's positive. If it goes clockwise, it's negative. So if we start here, that's what we call 0 degrees. And now we go positive 90 to get there, right? Because it's counterclockwise. Another positive 90 to get there, but now we overshot it. So now we have to go negative 45 to get there. So we have 180 minus 45. And so the angle from here to there has to be 135. Okay. And on like simpler problems like this, that's, you can probably just eyeball it, but we'll see problems where being like careful to yourself about making those jumps and counting those angles will really help you. Okay, so this angle then is 135 degrees. And then the third thing is the x component is the length of the vector, the magnitude of the vector, times the cosine of this angle. Let's call that counterclockwise angle theta for step 2. So L times the cosine of theta, and the y component is L times the sine of theta. And you can just, so for now, you can just plug those into your calculator. Yeah. Yes, we can. Okay, and or you can represent the whole vector in components like this. The whole vector's components are L times the cosine of theta, L times the sine of theta, with square brackets. So this is a useful way of writing the components of a vector, but we're not going to, in this class, we're not going to see how it's useful, but there's a lot of ways that this makes math easy to have it in this form. But the top one in this sort of matrix form is the x component, and the bottom one is the y component. Okay, so that's how to find the components, and that's mainly all we'll need to do, but I want to talk about what sine and cosine are a little bit. So that's pretty much all you'll need to do. But what are sine and cosine? The easiest way to picture what sine and cosine are is draw the coordinate system. And draw a circle with its center at the origin with a radius of 1. Probably the cool way to make on this, but I don't remember it. Okay. So let's say this circle okay, let's say that circle has a radius of 1. It's called the unit circle because of the radius of 1. And now for any angle, start at the positive x-axis and move counterclockwise that angle. You know, so let's say that theta is equal to 120 degrees. Okay, so we're going to start at the positive x-axis, rotate 120 degrees counterclockwise, so there, and draw that line. So this angle we'll call theta. Yes. So it's pretty much the same idea as what we were just doing for the vector components. Start with, like, imagine starting with a line that has a line segment that has a point at the origin, and then just rotate it, and then whatever number of degrees you want the cosine and sine for, rotate it that much. So then the cosine of theta is the x component of this intersection between that line and the unit circle. X component, the x coordinate, where the line hits the unit circle. And the sine of theta is the y coordinate, where the line hits the unit circle. Okay, so this, you can use this to just get sort of an intuitive idea of like what the sign, the plus minus sign should be for cosine and sine of certain angles. So let's think about if you have 120 degrees like I drew here. So I started at the positive x-axis, rotated 120 degrees, and so the cosine of 120 degrees is the x coordinate at that point, and the sine of 120 degrees is the y coordinate at that point. So is the x coordinate at that point positive or negative? Negative. And so the cosine of 120 degrees has to be negative. Okay. And then is the y coordinate at that point positive or negative? Positive. And so sine of 120 degrees has to be positive. What about like 200? So let's say we go to 260 degrees or something, right? So almost all the way to this. So we'd have a line going down like that. And so the point that matters is here. What would the x coordinate be positive or negative? Negative. And so cosine of 260 is negative. Would the y coordinate be positive or negative? Also negative. So sine of 260 is also negative. Other thing that isn't going to be useful in this class, but is often useful with sine and cosine is SOHCAHTOA. It's this made up thing. SOHCAHTOA. And the way it works is if you have a right triangle, you have a triangle where one of the angles is 90 degrees. And you're trying to figure out the trigonometric functions representing this angle. Then these are what the three legs are called. The diagonal one is always called the hypotenuse. That's the one that is straight across. That's the one leg that doesn't touch that right angle. You can think of it that way. And then of the two that are left, the one that touches your angle theta is called the adjacent. And the one that doesn't touch your angle, the other one that touches the right angle, is called the opposite. And then the sine of theta is the length of that opposite leg over the length of the hypotenuse. So if you look at that equation, SOH, that's the so. The cosine of that angle is the length of the adjacent over the hypotenuse. So that's the ka. Cosine is adjacent over hypotenuse. And then one we won't use, the tangent of theta, is the opposite over the adjacent. So that's TOA. So that's the TOA. So SOHCAHTOA reminds you what those fractions are that you can use to calculate sine and cosine and tangent. But we're not going to have to do that in this class. We're just going to be plugging stuff into calculators to calculate sine and cosine. It is helpful, though, the thing that I was saying about for a given angle, being able to figure out whether the cosine should be positive or negative, that's going to be a useful thing. So I would try to get in the habit of checking that mentally whenever you can on these problems. Any other questions about that right now? Okay, well, let's stop there.